Alright, what's this? 10.2. Now we're finally going to get into maybe a little calculus. So we're going to find a formula for dy dx, but that's a derivative on y with respect to x. And we're talking about parametrics, and aren't our x's equal to f of t, and our y's are equal to g of t or something like that, right? Well, there's a chain going on in here. Now let's start with this, because y is a function of t, and I know the notation seems weird and wonky, but this is how we get better with it, is we play games like this with parametrics and you start to get it. So then you're ready for your differential equations, your linear algebra, things like that. So let us talk about, maybe we want to know what's the derivative on y with respect to t. What's that equal to? Now I mentioned that it's a chain, so I'm going to write it down, and this is how we're going to get our dy dx. Since it is a chain, now typically, like, I'm just going to write off on the side, like y equals 2x minus 1, you know what I mean? And then in like algebra, we're like intermediate algebra, we're like, hey, call that shit f of x. And we're like, hey, look, f, it's a function of x. Now, isn't y typically a function of x? So we actually have a chain going on. I won't drone on about it forever, maybe for a little while, but we could say there's that dy dx times, and here comes the chain, the derivative on x with respect to time, because that's inside of there, right? That y is a function of x. We've shown that by putting the parametric equations together, where we can actually just put it all to where our y value is dependent upon our x, but both the x and the y values are dependent upon their t's. So that's the chain. The t is inside the x, which is inside the y. Why we need the chain, so I'm going to write something a little bit funky. I'm going to get rid of it right afterwards. But if we were to say we had f of g of x, right? And then we said, well, come on, y'all, let's just take a derivative on this thing. Wasn't that take a derivative on the outside? I know we left the inside alone. Don't just kind of ignore the g of x for right now. And then, so we took a derivative on the outside, that f function. Now I kind of got it backwards. I want to call it g of f of x just to make my frickin' point, but you know what I mean? And then we would multiply by the derivative of the inside function. Well, there's the derivative of the inside function. There's the derivative of the outside function. So that's the best I can do with trying to combine it and show you that it's tied with the chain. But here's our formula. Now let's clean this up a little bit, because we actually want to solve. We want to get dy dx. So we're going to divide out this dx dt. Now this seems kind of weird. So we're going to divide it out, and it's going to be dy dx is equal to that dy over dt divided by this dx over dt. Huh. Well, let's make sure that we write this down. We're all proper. So I think we could say this, that if all three derivatives exist, all three derivatives exist, then, oh, actually, hold on, wait a second. There's this thing that, oh man, oh yeah, and make sure that dx over dt doesn't equal 0. I mean, don't divide by 0. Then we could say that dy dx is just equal to the derivative on y with respect to t divided by the derivative on x with respect to t. And there we go. There's our little formula to get us going. So we can move that around now. I hope we're not trying to solve any dx dy's. Let's not get weird that way. You know what I mean? Let's make y. Think about that as our dependent, and our x is our independent variable. So we get our derivative, but let's keep going just a step further and follow along if you can. You know what I mean? We're gonna try and we're gonna try and knock this thing out. So if we have we want to find, say, the second derivative, and really wanting to get this in here so you can see that do not just assume it's the second derivative on y with respect to t and the second derivative on x with respect to t, because it is not going to be that. But really what this ends up being is we're going to take a second derivative on whatever we'd already found, our y prime. Our y prime is this thing right there. That y prime. I'm just going to write it as y prime. It makes it just a little easier to read this. But that's what I'm talking about, that dy dx, that derivative that we've already found, that thing. And what this ends up churning out, and I'll save some of it, is it's the derivative. Oops, I wrote it. Don't get weird. It's just that derivative on y prime divided by dt over the derivative on x with respect to t. So it's a second derivative, essentially almost on the y, but not. Notice that the derivative on x with respect to t, that is not taken on the second derivative. So this does not equal, it is not there. So with the same rules we had before, we can now state that the second derivative on y with respect to x is equal to the derivative on y prime over dt divided by the derivative on x with respect to t. And there's our second derivative, provided all the derivatives exist. And one more time, come on, we know dx dt, that shit can't equal 0, or else nothing's going to work out. And also we need y to be twice differentiable. Most everything is, but there might be some exceptions to the rule. So as long as we have these assumptions being true, we're good to go.